Hey all listeners, this is Prajesh Chaudhary, Quantum Guru. In this video, I'll talk about wavefront and its propagation. In recent year, in JEE-Advanced, question have been asked about the shape of wavefront in a medium in which refractor index varies, and also the divergence of a planar beam in the graded refractor index medium. So let's go ahead with a little bit theory. Theory is very simple. Basically, I'm concerned about the application. So I'll take two questions from JEE-Advanced and one very good question from SBT. So first of all, what is a wavefront? Wavefront in wave optics is similar to what is a equipotential surface in electrostatics. Equipotential surface is the locus of all points, a surface at which the potential is same, a locus of all points at which potential is same. In the same way, wavefront is the surface or locus of all points which are vibrating in same phase. So if you have some analogy between electrostatics and wave optics, it is very easy to understand the thing. So what is the role of electric field in electrostatics? That is the direction of energy in wave, and the EPS is obviously the wavefront. So rays are the lines along which energy propagates in a wave motion, and rays are always perpendicular to wavefront. So that is very important property. And one more very important thing is that suppose I have a one wavefront, and like this I can take say this is a wavefront, and this is another wavefront like this, and there are some rays. Suppose a ray is going like this, and this ray is going like this. So time taken from one wavefront to another wavefront through any ray is the same. In between the medium may vary, but the time taken from one wavefront to another through any ray is same. So that also means that the optical path from one wavefront to another wavefront through any ray is also same. So these are the things that we would be using for our analysis. So let's begin with a very good question of JEE-Advanced. That is from the 2020. You can see that in this question what is given, that this is a glass, this is a uniform medium glass, this is a air here, this is a air here, and a plain monochromatic light, a parallel beam of light strikes a surface of piece of a transparent glass having cross section as shown in the figure below. Correct shape of the emergent wavefront will be, and these are the options, and let's go ahead to solve this. So this is the diagram given. In this side there is air, outside the glass on this side also there is air. Now a plain beam of light is incident. I'll show wavefront like this. Because the beams are plane, this is a planar beam, so wavefront would be perpendicular to direction of propagation, so like this. And as soon as outside the glass, the speed of light is c, that is 3 into 10 to the power 8 meter per second, and within the glass the speed will become c by mu. Mu is usually 1.5, so that will be less than the speed of light in outside the glass. So now all the rays that were moving in air will start moving slowly. So still they will reach up to here. They will reach up to here simultaneously, because the same medium, the same speed, and they have to travel the same distance. So all the rays will reach to this wavefront simultaneously. At this moment, let's take few points on this wavefront. So these points. And let's take how much time the rays from this point will take to come out of the slab. Clearly this point has to travel the greatest distance inside the glass, and this point is immediately going to get out of the glass, and these 2 points and these 2 points will have to travel intermediate distance compared to this and this. So time taken to come out of the glass slab would be the greatest for this point and this point, least for this point, and intermediate for these 2 points. For a future moment when the ray from this point, say, has reached up to here, some time it has taken. In the same time, the ray from these 2 points or these 2 points will lag because they had traveled some distance inside the glass where the speed was smaller, so they will lag. So the rays coming from these points will reach somewhere here, and even more than them, the ray coming from these 2 points will lag the most. So at the same moment, the ray that has come from here will reach here, the ray has come from here will reach here. And now if I join them, I will get a shape of a wavefront at a future moment. So the shape of the wavefront at future moment when the rays has emerged out of the glass would appear to be like that. And now the direction of propagation would be such that this wavefront is perpendicular to that. And there is another way to look at this problem. So in this method, what we do, we divide this glass slab of various variable thickness into 3 parts. This is a middle part, this is the upper part, this is the lower part. So the middle part is like a diverging lens or the concave lens, and the upper part and the lower part are like the convergent or the convex lens. The property of the convergent lens is that when that lens is placed in a medium whose refractive index is smaller than that of the lens, it converges the parallel beams, and the reverse is the nature of this diverging lens, it diverges. So if I take few parallel rays on this part and similarly on this part, because of this converging nature, so the rays coming out of it after refraction will converge to this point, and this would be a kind of a focal point for this part of lens. Similarly, for this divergent lens, the rays coming out of the lens will be diverging, and they will appear that they have diverged somewhere from here, and the rays after coming out would be something like that. And similarly for the lowermost part would be the same as the upper part. And we can draw the wavefront for these rays. So here all the incident rays has emerged here. So if the wavefront would be something like a spherical wavefront whose center would be here, and for this part the wavefront would be something like that whose center would be somewhere here, and for this part the wavefront would be something like that. And if I draw that, so this is the wavefront for this part, and it would be spherical, center would be here, and wavefront for this part would be spherical, center would be at the point of divergence. And for this part also the wavefront would be spherical like that, and center would be here. And if we join all these with a smooth curve, we'll get the shape of wavefront would be something like that, and that would be the proper shape of the wavefront for the emergent ray. Alright, and now I have a very good question of JEE-Advanced 2023. The question states a monochromatic light wave is incident normally on a glass slab of thickness D. This is a glass slab of thickness D as shown in the figure. The refractive index of the slab increases linearly from n1 to n2 over the height h. Which of the following statement or statements is true about the light coming off the slab? So in option A and B, they are talking about how much angle the emergent wave deflect up, or option C, they're saying whether it does not deflect, and in what factor the deflection angle depend. So this is the diagram given. Is a slab of variable refractor index. The refractor index at this point is n1 and here is n2. The rays are incident like this. These are the wavefront before incidence on this side. Just before the rays are impinged upon the slab or the incident upon the slab, this is the wavefront. And now n2 is given to be greater than n1, so a speed of light at this point is smaller compared to speed at here. So by the time ray from here suppose reaches here, at the same moment the ray coming from this point will travel lesser distance because the speed at this level is smaller. So now at this moment, what would be the wavefront? So would the wavefront would be like this? If I assume this is the wavefront, so won't that be a contradiction that the wavefront is a perpendicular to the direction of propagation? So for that thing to not have contradiction, for that thing to follow, the ray has to bend up, something like that, so that now the wavefront can be perpendicular to that. So this d is very small, so we can neglect the bending, but it has to bend, right? And now, and once the rays have come outside, ray from this side and ray from this side has come outside the slab, the medium is homogeneous. In a homogeneous, the rays travel in a straight line. Like this was not a homogeneous medium, so ray in this part was a curved. Actually the ray is curved. For the approximation part, I have just drawn with a straight line. But once the ray from the both side have come out, they will travel in a straight line, and a straight line, and then the wavefront would be something like that. But from the level of n1, the ray is traveling faster, so it will come out first from the glass slab, and the ray at n2 level will come later, a little later. So meanwhile the ray from the n2 level is still inside the slab. The ray from the n1 will come outside and it will actually go in a curve, but for the approximation part I have drawn in a straight part. And from here, from the moment the ray from n1 level has come out, so for the already the ray had curved this way, and already the curving has become, and when both have come out of the slab, so they will move in a straight line, and perpendicular to their direction there would be wavefront. So now at this level, suppose if this is the wavefront, so perpendicular to wavefront there would be direction of propagation, and this curve, this part is actually something like this, and that is being approximated as straight line and straight line. All right, so from this wavefront to this wavefront, time taken by this ray and this ray is the same. So optical path from A to B is same as optical path from C to D to E, and that is what we will use. And this is theta, this is perpendicular, so that will also be theta, and this is h, so this is theta h, that would be h tan theta. So optical path difference from A to B is same as the optical path difference from C to D to E, and optical path is refractor index into geometrical path. So this optical path is n2 into AB, and AB is D, n2 into D, and optical path this is n1 into D, and this optical path is 1 into h tan theta, and just simplify that thing, we'll get tan theta is equal to n2 minus n1 d by h. So theta is equal to tan inverse n2 minus n1 d by h, and we'll get one of the option, and from here you can see on what factor this angle of deflection depends. All right, okay. Now we have also very good question. This is a very good question of SBT wave optics. This question says a parallel beam of light traveling in x direction is incident on a glass slab of thickness t. the refractive index of the slab varies with height y as a mu is equal to mu naught 1 minus y square by y naught square, where mu naught is the refractive index along x-axis and y naught is a constant. Again, because of the variable refractive index along y direction, the ray have to diverge or converge. Basically, it have to deviate, and they finally get focus at a point F on the x-axis by using the concept of optical path length. Calculate the focal length F, assuming that F is very large compared to T. Consider y to be small, right? So this was the slab, and on this direction the refractive index varies like this. Mu is equal to mu naught y square y naught. So as we go up along the y-axis or from the x-axis, as we go up or go down from x-axis, mu will decrease. Mu will decrease when the speed of light would be more as we go farther from the x-axis, either up or down. So we have these parallel beams. I have chosen symmetrical beam, and these are the parallel. The medium here is the air, so the wavefront would be the planar wavefront. So far the wavefronts are like that. And now see, the speed here is something, and the speed, we discussed that the speed here would be the most. The speed here is the least. The speed here and the speed here are the same, and the speed here is the least. So by some time, suppose the ray from here reaches here. In that time, the speed here is the more, so the ray would reach somewhere here. But just explained before, if I draw that thing, so this direction of propagation is not perpendicular to the wavefront, so wavefront would be curved, so that the direction is perpendicular to propagation. So from here to here, from this wavefront till this wavefront, all the rays will travel simultaneously. So from here to here, the rays will curved like that, and they will come out, and from here then they will come out like this, and now they will go outside. The time may not be the same. This is just to the not to the proper scale, and finally they will reach to at this point outside. So finally they converge here, and here the wavefront would be perfect spherical. This may not be spherical because here the medium was not uniform. So this would be perfect spherical, like this, and this is the point of convergence. So from this wave, and when at this point all the wavefront converge, so from this wavefront to this point, through all the rays reach simultaneously, through all the rays the optical path difference is the same. So for that thing I will choose either this ray or this ray, and I will equate the optical path difference, and that will give me the focal length. So let's take this diagram. So from here to here and here to here, we have two paths. Optical path difference should be the same, and mu is this. So the points are, this is A, this is B, this is C, this length is T, refractive index here is mu, this is D, E, and this was C, and C was basically F focus. Refractive index here is mu naught, and this distance is the focal length F. So optical path difference from A to B to C is same as optical path difference from D to E to C. So equate those things. So this is mu into T, and here is the air, so 1 into BC, and that BC is a square root of y square plus f square, that is this equation. And this thing is a mu naught T plus f, and just rearrange the things. So y square plus f square minus f is equal to mu naught minus mu into T. So here from both of these take f common, So f common inside bracket, there would be 1 plus y square by f square and minus 1, and for that thing you can apply the binomial approximation. Y is very small compared to f, so this thing would be 1 plus y square by 2f square, and minus 1 and minus 1 will get cancelled. And here what I have done, I have just put the value of mu. So mu minus mu naught is equal to mu naught y square by y naught square t. Well, if physics is done, you can do your own calculation. So just simplifying these things, we'll get f y square by 2f square is equal to mu naught y square t by y naught square. This y square will get cancelled, and just rearranging, we'll get f is equal to y naught square by 2 mu t, and that would be our answer. Thank you.